Yes, hello. My name is Johann Zirngibl. I am from the Scientific and Technical Building Center in France, which is a public research institute and belonging to the French Ministry of Construction. I'm very much involved in European and ISO standardization, where I'm the convener of several working groups. And here I am talking as a convener of working group TC228, working group 4. So just to start about this, heating and water-based cooling systems, you should know now, because my colleagues presented already several times, this overall modular structure, where all the European standards under Mandate 480 are represented. And here I show you the standards of TC228. So you can see that we have several standards. For example, we have standards linked to the needs and the maximum loads. So this, for example, here for domestic hot water. Here you have the tapping patterns, which are very much important for energy calculation. And also here you have, for example, our standard on for sizing the heating meters and the boilers. This one is one of our standards, which is very much used all over Europe. And then the other ones where I will talk a lot more about here today is the standards which are related to the energy calculations of heating systems in buildings. So here you have emission and control, distribution, storage, and generation. And we have a lot of standards related to this generation. Here the green ones are those who are related to renewable energies also. For example, for combustion boilers, we have also biomass boilers, and we have heat pumps, thermal solar, also photovoltaics. And we have also district heating and cooling, of course, where you can have a renewable part. And the others you can see also on them. And then in TC228, we have again other standards. One is related to measured energy performance. Here we have the numbers of it. Another to inspection, and another one to economic calculation, for example, about payback times, global costs, and things like this. But as I said before, I will focus on the energy calculations. So, and here again, it's just if you want to have some more additional information, this makes a link with the table before to give you here. You can see here you have the standard numbers, and here you have the title, so it is easier to remember. Here you have the modules numbers, and here, as it has been shown before by my other colleagues, here you have the task leaders. So if you have some contributions or additional questions, you can contact them directly. So the TC228 Working Group 4 standards are reflecting the physical structure, because they have the needs, and then you have the emission part. The emission part here, you go to the distribution, you go to the storage, and then you have the general parts, the generation parts like different boilers or the solar parts. And here you have again the different standard numbers. So where is the position of these standards within the general frame? You may know that the general frame of all this is a PREN 15603. So in 15603, it's reflecting also the overall system. So it goes here, for example, if you see the energy direction, the energy flow, who goes from the primary energy, so from the source to the demand, so it goes to the building, and then you have generation, storage, distribution again, and then you have the losses, the energy goes out. And here you see that the calculation direction which we have in this overall energy calculation is that we go from the building needs to the energy rating, so it goes the other way around from the demand to the source, and all the TC228 Working Group 4 standards are calculating the system losses, so the things which are going out at each, let's say, subsystem. So I just wanted today, in the short times we have, I just wanted to show you some main principles about the different parts. for example, the emission part, the distribution part, the generation part. So here I start with the standard 15316-2, which is related to emission, and the principles are here. So we take into account some effects which are due to non-uniform temperature distribution. So, for example, you can see here, if you have the temperature, the very vertical temperature distribution within a building, within a room is different. If you have, for example, a floor heating system, or if you have a high temperature emitter, and these things are taken into account, the stratification is taken into account in our calculation method. Then we also take into account the position of the heat or cooling emitter. So it's here, for example. So here you have some, let's say, losses to the outside, and here also, so if it is embedded, and also if you have here an emitter, so we have much more losses going out behind. For example, if it's not very, if there is no additional insulation or things like this, and these are also taken into account in the losses when we talk about the emission part. So this is linked to the physical structure, let's say, and then you have also the effect on control accuracy. So it's showing here, so depending on the quality of your regulation, so it goes up and down. So we have a delta T, and these things are also taken into account. And then, for example, we come to an equivalent increased internal temperature, where you have all these different things reflected in different delta T's, which are added to their internal temperature. What I also wanted to underline is that this approach is very much linked to product certification. And here again, we have a strong link with the Eco-Design Directive. And for all our standards within TC 228, we underline this very strong link with the Eco-Design Directive. The next part is the distribution. So here again, the thermal losses of a distribution system, are calculated by a very basic equation, which is linked to the coefficient and the delta T and the area of the pipes. So, and of course, for this, you need to have the length of the pipes. And for example, to have the length of the pipe to calculate the distribution losses, we have some simplified input correlations. For example, you have the building, and we have different typologies and systems, and then you can calculate the length of the pipe with some equations we have developed. And here you see this equation is linked to the maximum length of an emission system, and this maximum length of the emission system we take into account for the distribution system, we take into account to calculate the auxiliary energy, so the electrical energy of the pumps. And here we distinguish also, we take into account also the control, and we take into account, for example, if there is no control or if there is speed control or things like this. So these are mainly the points we take into account when we are talking about distribution losses. And then the next point is, for example, linked to our generators. So what we want to do is here, we want to identify the load performance curves for thermal efficiency and electrical output, if it is, for example, a cogeneration unit. So before, in my overview, I showed you that we have also cogeneration units there. So here you have something like, here it is electrical output on the load of a device, and here you have the thermal efficiency. So these things are also related to product testing. And so what we do is to calculate the heat losses. We do not interpolate the efficiency curves, but we interpolate the losses because they are much more linear, so the interpolation is more easier and more precise. And we just we take the product data and then just we make the extrapolation between the different product data we have. For example, here for the standby losses, or here for the, let's say, for the load, for the losses at 100% load, and then we just interpolate it in a linear way to have the losses of the generation units. So what I wanted to show also is, for example, the storage one. So here you the storage principles. So here I showed you on the screen, you see domestic hot water scheme. So here you have a tank, the storage tank, and you can see that within the storage tank you have, for example, connected. Where is my pointer? Here it is. Yes, here you have connected to, for example, here you have a thermal solar panel, and here you have a backup heater. So you see that it is not connected at the same height within the storage tank. And this has a very strong influence on the energy supply, because the stratification linked to the domestic hot water use is very much important. So, and this will have a very strong influence on the different systems used of your, for example, the contribution either from the solar part or either from the backup heater. So this is very much important, the stratification and also the tapping patterns, which I showed you in one of our first standards. So this is why, because to take into account this dynamic evolution and to take into account the stratification, we developed a dynamic multi-layer model on an hourly base step. So here it is just the principle of the layer. We have 4 layers and the different energy supplies. For example, here is connected one. This could be the backup boiler, or here's the thermal solar. So we can connect directly the different supplies at the different layers. And here I don't go into the detail. You see the energy balance for each layer. So this storage model is very much related to domestic hot water and not so much to buffer tanks. And also what we do not take into account is, for example, it's only a water model and not a phase-changing model. I think phase-changing models are more important for cooling storage. And now, okay, very shortly, because I'm a little bit over time, and you will see here that we have also something very important in the district heating standard, which is linked to the primary energy factors. So you may know we distinguish, this is also linked to 15603, but we have it also in our district heating standards. Here you can see we distinguish between the total primary energy factor, the renewable the non-renewable primary energy factor, and the renewable primary energy factor. And here you see how it is taken into account to calculate the primary energy factors. It is, let's say, the expenditure between the delivery, here is the billing side, and between the source of the energy carrier. It's this ratio. And the different details are given here with a number, so we can follow it. And I come to the last slide now, is how the renewable energy is taken into account, and here in our standards. And here I give you the example of a heat pump. You see that here you have a heat pump, you have the electricity coming in, you have the ground heat exchanger, so this is the energy captured by the evaporator, and then here you have the energy output. And what we take into account in the renewable calculation, we have the physical approach, where we take into account, for example, the energy from the heat exchanger, from the ground heat exchanger, and just we make the ratio of this to the total primary energy, which is shown on this example. And the values here, these are the primary energy factors to the different energy carriers, the renewable part and the total part. Okay, and then you have the RER ratio, renewable energy ratio, which in this case is 51%. Okay, thank you. Sorry for a little bit overtime.